know that the p block elements are placed to the right side of the periodic table in groups 13 to 18. You also know that in the atoms of p block elements, the differentiating electron enters the valence p subshell. Thus, in these elements, the NP subshell is gradually filled. On account of this, the general valence shell electronic configuration of these elements is NS2, NP1 to 6. Note that the electronic configuration of helium is 1s2. Although helium does not have p orbitals, it is a p block element because it resembles that of other p block elements of the 18th group with respect to their properties. Most p block elements are non-metals, while the remaining are metals and metalloids. Thus, the presence of all the three types of elements in p block of the long form of periodic table bring diversification in chemical behavior of these elements. The study of these elements is an important area in chemistry, as these elements and their compounds have immense significance in industries and day-to-day life. Now let us turn to the study of group 15 elements. Let's first discuss the occurrence of these elements. The elements in group 15 are nitrogen, phosphorus, arsenic, antimony, and bismuth. Nitrogen is the major constituent of the Earth's atmosphere and accounts for 78% of it by volume. It is the first member of this group and occurs in free state as a diatomic gas, N2. No other element of this group exists in free state. In combined state, it mainly occurs in the form of minerals such as Chile salt petre and Indian salt petre. It is also found as the essential constituent in proteins, amino acids, nucleic acids, and enzymes. The next element in the group is phosphorus. It is the 11th most abundant element in the Earth's crust. Being a very reactive element, it does not occur in free state in nature. In combined state, it occurs in the form of minerals as phosphates. Chloropatite, fluorapatite, and hydroxyapatite are some examples of phosphates. These comprise the apatite family. Phosphorus is an essential constituent of plant and animal matter. Phosphate groups are among the important constituents of nucleic acids, that is, DNA and RNA. About 60% of bones and teeth are composed of phosphates. Phosphoproteins are present in egg yolk, bone marrow, and milk. The remaining elements of the group, that is arsenic, antimony, and bismuth, mainly occur as sulfides. For example, arsenopyrite, stibnite, and bismuth glands. Now let's look at the electronic configuration of group 15 elements. The differentiating electron in these elements enters the NP subshell. Hence, the valence shell electronic configuration of these elements is NS2NP3. So, it is evident that these elements have 5 electrons in their valence shell. The electronic configurations of these elements are listed in the table here. Due to the exactly half-filled electronic configuration of the NP subshell, the elements of this group are fairly stable. For example, dinitrogen is an inert gas under normal conditions. Now, let's look at the trends of some atomic properties of group 15 elements, such as atomic and ionic radii, ionization enthalpy, and electronegativity. A comparison of these two tables shows that as we move down the group, the atomic radii, covalent radii, and ionic radii increase due to the addition of a new principal energy level in each successive element. There is a considerable increase in the covalent radius from nitrogen to phosphorus. This is due to the effective shielding of the s and p electrons present in the penultimate shell of phosphorus. However, from arsenic to bismuth, there is only a small increase in the covalent radius due to the poor shielding effect of the d electrons of the penultimate shell in arsenic and antimony, and the poor shielding effect of the f electrons of the antipenultimate shell in bismuth. As a consequence, the effective nuclear charge increases, which leads to a small increase in the covalent radius from arsenic to bismuth. Now let's look at ionization enthalpy. Group 15 elements show higher values of ionization enthalpy as compared to group 14 elements. This is due to their higher nuclear charge, smaller atomic radii, and stable half-filled electronic configurations. However, as we move down the group, the value of ionization enthalpy decreases. This is due to the gradual increase in the atomic size, which reduces the force of attraction between the valence electrons and the nucleus. Finally, let's look at electronegativity. You know that electronegativity is the tendency of an atom to attract a shared pair of electrons more towards itself. The values of electronegativity of these elements are listed in the table here. As you can see from the table, the electronegativity decreases gradually on moving down the group from nitrogen to bismuth, due to the corresponding increase in the atomic radii. Note that after fluorine and oxygen, nitrogen has the highest electronegativity. Let's first study the physical properties of group 15 elements. Physical properties include physical state, metallic character, melting and boiling points, density, and allotropy. Let us look at each in turn. Nitrogen is a diatomic gas, while the remaining elements are solids. You know that as you move down a group, metallic character increases. The same trend is observed for group 15 elements too. Do you know the reason? Try to answer this question on your own before looking at the answer. As you move down the group, the ionization enthalpy of the elements decreases with an increase in their atomic size. In other words, the effective nuclear force of attraction on the valence electrons decreases down the group. As a consequence, the metallic character increases down the group. The first two elements of this group, nitrogen and phosphorus, are non-metals, and the next two, arsenic and antimony, are metalloids, while bismuth is a typical metal. Next, let's look at the trends in melting and boiling points. The melting point increases from nitrogen to arsenic due to the gradual increase in atomic size. The very low melting point of nitrogen is due to its discrete diatomic molecules. On the other hand, the high melting point of arsenic is attributed to its giant layered structure, in which the layers are closely packed. However, although the atomic size increases from arsenic to antimony, there is a decrease in their melting points. Although antimony has a layered structure, it has a low melting point than arsenic because of the relatively loose packing of atoms. Furthermore, the melting point of bismuth is less than antimony.